So this will be a conceptual introduction to the concept of flux and a build-up to Gauss's law. We'll do Gauss's law examples in class. Now, we'll start with the concept of flux, which we've already seen in the prerequisite course in Physics 12, where we defined magnetic flux as the amount of field passing through a surface. And we found that the amount of flux depended on the field, strength of the field, on the area of the surface, but there was also an orientation factor, just to reflect whether the field was cutting through the surface, straight through the surface, or perhaps on an angle, or perhaps not at all. As you can see here, this field is just tangent to the surface, so there's actually no flux at all in this case. So mathematically, the magnetic flux was the strength of the magnetic field, the surface area of the surface, and then the cosine of the orientation angle, where theta was the angle between the magnetic field vector and a surface vector that we call n hat. So this is an outwards pointing surface vector. Now this will become a lot more important when you do calculus 3, but for now, so outwards pointing surface vector, that's what n hat is. Okay, so if we look at, say, a spherical surface, and then imagine this is the magnetic field vector, B, the darker arrow is the B vector, then in this case an outwards pointing surface vector would be like this. And so now these two are in the same direction, so that would be an angle of 0 degrees. Now B goes inwards, cutting into the surface. Our outwards pointing surface vector is this way, so that's an angle of 180 degrees. And so cos of 180 is negative, so inwards flow opposite the surface vector is negative flux. Here, with the field tangent and just sort of skirting along the edge of the surface, the angle is 90 degrees, and there's no flux at all, which makes sense because the field isn't actually cutting into the surface. So this is a recap of some things that you once knew about magnetic flux. With Gauss's law, we're interested in electric flux, but we can define it in a similar way. We can say it's a field times an area times an orientation factor, although the field we're talking about is now the electric field. So the units here, electric field is in newtons per coulomb, and then area is in square meters. So we get these awkward units. Now, in calculus 3, you'll be introduced to a surface integral, and we can actually write flux in a more sophisticated way using a surface integral. This is a special integral, so we put a little loop here just to indicate that we're not doing a normal Riemann sum. We're actually adding things up over a surface, not adding things up as we walk along the x-axis. So what we're going to add up over the surface is the electric field times a little bit of area, and then there's a dot product there, a vector dot product to keep track of the notation. So this is how we'll define the electric flux. So that's a phi for electric flux. E is electric. But the good news is we won't have to actually do any surface integrals, because for the symmetric surface, for the right surface, this is just going to end up being what we have above. And so we just have to always ensure that we have a good symmetric surface, and we'll describe what we mean by that shortly, so that we can actually calculate the flux in an easy way, because we're just not ready to do surface integrals yet. So this is E times A. That's pretty messy, but that's what it is. It's E times A. It's not letting me erase. There we go. Okay, so this is flux. Let's do some flux examples. Okay, so here we have a charge. This is a real charge. And then let's find the flux through an imaginary surface. So this is an imaginary sphere. The sphere has radius 2 meters. And this is a point charge. We don't know the size of the point charge, but it's relatively small. So, well, first we need to know the field strength. Now the field strength will be everywhere the same on this surface, everywhere 2 meters from the charge, and you find it using kq over r squared. So there's kq over r squared. So you get 4,500 newtons per coulomb of electric field 2 meters away from that charge. Now, the area of a sphere, you may recall, is 4 pi r squared. So if we put in 4 pi times 2 meters squared, we get 16 pi square meters. So now, because this is a positive charge, we know the electric field to be pointed away from it, everywhere away from it. So that's electric field E. And I'll just change colors, and I'll just draw the outwards pointing surface vector. So the outwards pointing surface vector, you can see the electric field is going to be parallel to it. So now when we go to calculate the electric flux electric, we're going to add up over the surface the electric field dotted with a little bit of area. Now, since the electric field is everywhere parallel to that outwards pointing surface vector, the first thing we can do is we can drop, that loop is supposed to enclose around the integral sign, we can drop the dot product because E is parallel to n hat. Okay, so you get to drop the dot product. Then, because the electric field is everywhere constant over this imaginary surface, constant things can come out of integrals. All right. Finally, if you add up a little bit of area, dA, all over the surface, you get the total area of the surface. So on the previous page, we said, hey, you'll never have to do a surface integral if it's for a symmetric surface. This is the sort of process that we mean. So now we can put in the values here, and we get a value for the flux, and it's 226,000 about Newton meters squared per coulomb. So that's the flux through this imaginary 2-meter radius sphere. Now what if the sphere went out to a radius of 4 meters? Okay, well, the electric flux in that case would be adding up over this imaginary sphere, the electric field dotted with a little bit of outwards pointing area. Firstly, the electric field over this imaginary sphere would be parallel to the area vector, to the outwards pointing surface vector, so you can get rid of the dot product. The electric field is constant over the surface, so you can pull it out of the integral. Adding up little bits of dA over the surface gives you the total A, or the total area of the surface. All right, now we're 4 meters away from the charge, so this is going to be kq over 4 squared. But now the surface area got bigger as well. It's 4 pi r squared. R is now 4 meters squared. Notice that cancels out. Notice the distance cancels out altogether. We just get 4 pi k times q. That's going to be exactly the same value we had before. So this is something that sort of pauses and makes us go, the same flux. So the flux didn't depend on the imaginary surface we picked, right? We could pick a radius of 8 meters. You'd still get the same flux. It's independent of the imaginary surface. All it depended on was the charge present. This ultimately, this is foreshadowing. This is what Gauss's law tells us. Okay, but let's not get too far ahead of ourselves. Let's just practice a little bit more calculating some more fluxes. Okay, so here we've got an imaginary cube. Okay, it doesn't look like a cube, but my drawing program was primitive at the time. There's some electric field coming in at the top and some electric field going out at the bottom. The electric field does not cut through the sides. Right, the electric field is parallel to the sides. So here we've got negative flux on the top, positive flux on the bottom, because outwards flow is positive, and no flow on the sides. To find the electric field, you actually have to consider all the surfaces. Okay. Sorry, to find the electric flux, I don't know if I said that right. To find the electric flux, you need to consider all surfaces. All right, so how do we do it? So we're going to add up E dot dA. So this is area in the direction of the outwards pointed vector. So I should say that, just in case those of you who are mathematical will be wondering. So what's the dA vector? Well, it's a little bit of area in the direction of the outwards pointing surface vector. So this is sort of a Cal 3 thing, and it won't really matter to us too much because we're always going to reduce this to something a lot simpler. So first of all, we'll break this up into 3 terms. First of all, the top, then the bottom, and finally, I ran out of room there, hopefully you still got room, over the sides. Now over the top, because the vectors are opposite, the dot product gives -1, and you end up with a constant electric field that comes out. Adding up the area is the area of the top, and the area is just 1 meter squared for each surface. On the bottom, the vectors are in the same direction. That's not equals, it's plus. And so the dot product gives +1. The electric field is constant, so it comes out. And then we multiply by the area of the bottom, which is the same 1 square meter. On the side, because the electric field vectors are directed downwards, they're perpendicular to the outwards pointing surface vector, and consequently the dot product gives 0. So there's no flux through the sides. So substituting in the value of 17,000 on the top surface and 9,000 on the bottom surface and the 1 square meter of area, we get a net negative flux of 8,000 Newton meters squared per coulomb. So that's our second calculation of electric flux. Now, what if we tried to find the flux through a cube, so sort of like the previous example, an imaginary cube, with a point charge at the center? So that's kind of putting the first 2 examples together. Well, we know that flux, electric flux, is adding up field times area over this surface. Can we do that? Well, it turns out to be very difficult to do. Here's why. First of all, with this point charge, say up here at the top surface, the electric field will be pointing straight out. So that looks pretty good, right? And then you say, okay, so it's a meter, so if the charge is at the center, this is just a ½ meter away. And you might be tempted just to proceed with calculating it like we did before. But you've only considered the electric field at this one point. If you look, say, maybe over here a little bit, suddenly the electric field is not cutting perpendicular through the surface. And even more troubling, the distance is different to the charge. You're no longer a ½ meter away, so the electric field intensity is actually different here. So the electric field is not constant over this surface. And the angle is the angle between the electric field vector and our outwards pointing surface vector. Changes, it varies over the surface. So it's not possible to do this easily in Calculus 2. Now in Calculus 3 you'll find a way to do these surface integrals anyway that take account of these 2 problems. But for us, this is really hard to do. So you can't do this easily. It's still true. It's still true. That's our definition of flux. I should say it's still true, but you can't do it easily. So this just tells us that you have to pick the right imaginary surface to calculate the flux. And in example 1, we used a sphere. And over the sphere, it was easy to find the flux created by that point charge. But with a cube, it's not easy. So this is what we mean when we say pick a symmetric surface. The symmetric surface should have a constant electric field everywhere over its surface, and it should have a same angle between the electric field and the outwards pointing surface vector, usually 0 or 180 degrees. Let's consider a final example of calculating electric flux. Let's imagine we have a line of charge. Now, what would be an appropriate symmetric surface in this case? Well, a cylinder will have the appropriate symmetry. The electric field, if this is a positive charged wire, will be everywhere away from the wire. And so you see that that electric field is going to cut very nicely through the walls of the cylinder. So if I imagine a point right here, the electric field will be cutting nice and perpendicular through that surface. There's my outwards pointing surface vector n hat. And so for calculating the flux, we have on the walls of the cylinder an easy time of it. Now, we also have to consider, though, the flux through the ends. The end surface right here. Now the good news there, though, is that because the outwards pointing surface vector is this way, the electric field you could see is perpendicular to that. Or in other words, another way of putting it is just that the electric field does not cut through the ends. So there's no flux through the ends, there's only flux through the walls. Now, if we make this cylinder concentric with the wire, the electric field will be constant over the walls, and therefore you can pull it out of the integral and you can proceed to evaluate the flux in that way. So the first thing I said was that this electric field was zero because the flux doesn't cut through the ends. The next thing I said is, okay, this angle is 0 degrees, they're parallel to each other, so the dot product disappears. Then the electric field is constant, so that gets pulled out because we're everywhere the same distance from the wire of charge. Then adding this up just gives us the area, but we need to be a bit more specific. It's the area of the cylinder walls. Now, what is the area of the wall? Well, it's 2 pi r times the length L. And so our cylinder had radius of 5 centimeters and length 50 centimeters. And the electric field intensity was given in the question as 1,000. So we can find the flux. It's 157 Newton meters squared per coulomb. So our analysis thus far has given us the tools that we need to calculate electric fluxes for common symmetries, shown the necessity of a symmetric surface, and also pointed towards a relationship between flux and the enclosed charge. That is the basis for Gauss's law, and that's now that we can calculate fluxes where we're going to turn our attention to. So, what Gauss's law states is that you get flux when there's enclosed charge. You get flux through an imaginary surface if there's charge inside that surface. As an example, let's consider two charges. So here's a positive charge. Oh, that was messing it up. I didn't want to mess it up. That's a positive charge. Here, maybe I'll circle it like that. So that's a real charge. And here's a negative real charge. And everything else is just imaginary. Those are the only two real things in this problem. Now, let's consider some surfaces. So here's a surface 1. Now we know that there'll be electric field that's going to go away from this positive charge, and it'll actually, the electric field pattern, it'll bend around and go towards the negative charge, right? So this is what the electric field pattern is going to look like. And then we draw these electric field lines like this, all like that, sort of. Okay, perfect. So for imaginary sphere 1, is there net flux? Yeah, there's outwards flux, there's positive flux. So I guess the answer is yes. It's positive because it's outwards. The electric field is parallel to the outwards pointing surface vector. Let me drag that over. Oh, not going to drag. Okay, smartboard failure here. So the answer is yes, there's net flux. It's positive. Is there enclosed charge? Yes, there is. And there's a positive enclosed charge, right? Inside this first imaginary sphere, there's a positive charge. Next, we look over here at this second imaginary sphere. Is there net flux? Yes, there's net inwards flux. Inwards flux is negative. Is there enclosed charge? Sure. Notice that it's a negative charge. So you're beginning to see a proportionality here between the net flux and the type of enclosed charge. Okay, the third imaginary sphere here, we notice that whatever field line enters it also leaves it, so there is no net flux. okay? But there's also no charge enclosed by that sphere. There's just empty space there. Or how about for 4? Well, for this larger imaginary sphere, again, we notice that every field line that goes out also goes back in. So there's 0 net flux. Because these two charges are equal to each other, there's also 0 net enclosed charge. So again, we observe a proportionality between the net flux and the enclosed charge. This then is what Gauss's law tells us. It says that you get electric flux through a surface when you have net enclosed charge inside the surface. Mathematically, it says that the electric flux, and I've bounced back and forth between using a capital phi and a small phi. That really doesn't matter. You get electric flux through an imaginary 3-dimensional closed surface when you have net charge enclosed by that imaginary surface. So this is the statement of Gauss's law. So we'll clean up a couple of things that we've skipped over here, and then we'll do some examples with this in class.